So welcome to MAT, whatever it is, hour 27. Homework 8 will be on the web by midnight tomorrow. Probably tomorrow because I'm overloaded today, so I probably will not have time to write it. Also, I again apologize for the delay in marking. Part of it is because one of you wrote a lovely solution to question 1, I think, of homework 5, wrong solution. But it took me a long time to figure out where exactly is the mistake. I spent about a week on that. It's wrong, but extremely close to right. And it got me to the point that I started suspecting that math is inconsistent. Because, you know, you do something wrong, you get the wrong answer. You do something which appears completely right, and you get the wrong answer. And then you do it in a different way, and you get another maybe right answer, or maybe wrong. Then that's math inconsistent. So, anyway. So today we will do a bit more about quandles, just a bit, because the truth is that I don't know much about quandles, and in a sense, probably not too many people know much about quandles. Probably there isn't much known about quandles. So I'll do just a little bit more about quandles, and then, good, what do manners say now? One person dropped out. Okay, so I'll say a little bit more about quandles and then start talking about Seifert surfaces. But before that, a correction. So last time I got kind of excited and there was a little time left, so I ended up saying something completely wrong. So let me correct it. So last time I said that the add z from L to L, so the adjoint map, so from Lie algebra to itself, just to be clear, the adjoint map from Lie algebra to itself is defined by add z of x is equal to x bracket z. So I said that this is a morphism of Lie algebras, and this is complete nonsense. I was just running too quickly. Okay? The correct statement is as follows. So, okay. Really, the statement about quandles is that the quandle map from Q times Q into Q is equivariant, which means that, well, if you have Q times Q going to Q via the quandle operation, the up operation, and then a second line in which Q times Q goes to Q via the up operation, and then you have vertical morphism. So a morphism, a map from Q times Q into Q by multiplication on the right, where by a fixed element z, where multiplication on the right, when you act on a pair, is interpreted as you multiply each element of the pair. So in other words, you extend the right action of z on q to q times q by acting diagonally, by acting on both elements in the same way. Okay? And here on the right, I have again multiplication on the right by an element z. And in fact, maybe I shouldn't be calling it multiplication. I should be calling it the up operation. I mean, this is what it is. It's just the up operation. Okay? And then the claim is the quandle axiom, or the self-distributivity axiom, is the fact that this square is commutative. And now I want to translate it to the infinitesimal world. So in the infinitesimal world, I'll have L tensor L going to L using an operation called bracket, and I'll have L tensor L going to L using the same operation called again bracket. So this is also bracket. And I'll have the vertical maps, and the vertical maps are add Z, which really means, as I've defined here, bracket on the right with Z. So this is the precise analog of up Z here, except add Z get extended to pairs, to the tensor product, by Leibniz's rule. So add Z acts on X tensor Y, maybe I'll write it, add Z acts on X tensor Y by adding on the first one or acting on the first one or acting on the second one, and then add the results, but not this, but do not act on both of them at the same time. So in other words, this is add Z of X tensor Y plus X tensor add Z of Y. And if you've seen how tensor products of representations of Lie algebras are defined, this is exactly how the tensor product. So this basically means that I'm taking L tensor L using the tensor product structure as a representation of L itself. Anyway, the claim, so the analog, the infinitesimal analog of the self-distributivity axiom is that this square will be commutative, and this is indeed the Jacobi identity. The commutativity of this square is the Jacobi identity, and the comment to make is that the statement lying here is not that add Z is a morphism of Lie algebras, but that the bracket is an intertwiner of representations of Lie algebras. So the correct algebraic statement is different than what I said. Apologies. Also, I don't know why, but again, I'm having a slow day, so the computer is reacting slowly to my hand motions. So, okay, a few more words about quandles. And I'd like to emphasize, I don't know much about quandles. Yes, Leonard?
I don't know if, so the screen is not updating. I'm having trouble looking at the screen. It's blurred for me, so I don't know. The screen is not updating. The shared screen.
The shared, is it updating?
For me either.
What? It's not updating for you either?
Yeah.
Yeah, not for me either.
Okay, sorry, let me unshare. Sorry, let me stop the share and start again, and maybe that's related to why everything is slow. Ooh. Wait. If things die, then please reconnect in a minute, because my computer is just not responding. Or not quite not responding, but yeah. Let me stop the video, I'll start it. Yeah, so as I said, I don't know much about quandles myself, but here are a few facts. So first of all, so here are a few ways to get quandles from various places, okay? So the one we've used so far is if you have a group, then you can define x up y to be y inverse xy, namely x conjugated by y, and that satisfies the quandle axiom. So the self-distributivity axiom. It's a bit odd, but you can also do x up y equals y to the minus n x times y to the n, where n is some integer, and that's again a quandle. You can check, you can just, verify, and it's not. Well, it's a different way of getting quandles from group. Each of these ways, so this is conjugation by y to the n, so it's still conjugation, but it's a different conjugation. And so, but each of these can be restricted to conjugacy classes. Okay? Then there is a weird way to get a weird quandle operation. So you define x up y to be yx inverse y. And again, direct verification tells you that this is a quandle. I have no idea where it's coming from. I have no philosophy behind it. You just verify. I don't know what to say. Then there is a certain a paper that I found on the web by a fellow Vendramin, and Vendramin, by brute force, computed the number of non-isomorphic indecomposable quandles. So I guess there is a direct sum operation for quandles, so the ones that are not direct sum, for number of elements running up to 35, and here are the numbers. Okay? And I think most of these have nothing to do with group theory. They're just sporadic quandles. I don't think there is a theory, like there is the theory of groups, has, you know, every group can be decomposed into a tower of extensions by simple groups and such things. I don't think there is any theory behind quandles. He does make a lovely condition, so a lovely conjecture, sorry. So if you look at twice a prime number other than p equal to 3 and 5, so basically if you look at 7 times 2, that's 14. If you look at 11 times 2, that's 22. If you look at 13 times 2, that's 26. And if you look at 17 times 2, that's 34. Then there are 0 quandle of that dimension. For all I know, nobody knows why. So basically there isn't a theory of quandles. There is a little bit of odd, esoteric, random information, but for all I know, there isn't a developed theory. Nevertheless, there is a whole book about quandles, but this is more about how to use quandles in knot theory. I don't think there is a developed quandle theory in this book, and sorry, I said I will need a minute, and I do need a minute right now. So I need to, I think the issue is that my computer has run out of disk space, and I need to clear some. Yeah, okay, hopefully now it will go a bit faster. Anyway, so there is a whole book by El-Hamdadi and Nelson. You're welcome to look it up. It's on, I mean, you can find the versions of it on the web. There is, oh, I should have said maybe even earlier that there is something called the fundamental quandle of a knot. So the fundamental quandle of the knot is just like the fundamental group of the knot, but in the world of quandles. So in other words, you define Q of K to be, this is still slow, I'm not sure what's going on. So you look at the same generators and relations as in the Wirtinger presentation. So you look at the group generated by AI, where I is an arc, where the AIs are in bijection with the arcs, modulo relations of the form A is equal to, but instead of writing A, B conjugated by C, you write B up C. And this is, you do such a thing for one for each crossing. For each crossing. And, but now, instead of looking at it as the group generated by the AIs with these relations, you look at it as the quandle generated by. So what does it mean? You look at the free quandle generated by the AIs. What is the free quandle? You just allow yourself to take all possible quandle operations beginning with the AIs. Okay? And then you mod out by the relation. So it's essentially the same definition, the same construction as the group generated by some generators and relations, except you do it in the world of quandles. So in fact, this appeared in the first paper on quandles, which is by a fellow Joyce. And in fact, Joyce proves that the fundamental quandle of a knot determines the knot. So it is even a bit stronger than the fundamental group. Still, the word problem is insoluble. And then the last thing I wanted to say is that you can go on beyond quandles, and here is a picture that appears in the El-Hamdani Nelson book, but I actually took it from a paper by Aksoy and Nelson, and here is the reference. So basically, well, it's roughly like groups. So near groups there are various things which you get when you relax various axioms. So there are groupoids and monoids and magmas, and I don't know, maybe there is more. So in a similar way, near quandles there are Ks and BKs and racks and B-racks and God knows what else. Okay? And the only reason I'm showing it is for fun, because I actually don't know much about these things. Maybe I'll just say, I'll only explain what the B stand for. God, everything is half dead. That's not a good... Sorry. So I'll just explain what the B stands for in these cases. So you see, the way we derived quandles was, we said, given a crossing, we are looking for colorings that have the property that if the bottom is colored A and B, then the A color goes undisturbed through the crossing. So maybe you call it, so this one is also A, and the B color gets, and the B color gets acted on by A. So here you'll get B up A. But that's artificial. I mean, equally well, you could look for operations in which B will act on A. So maybe you should be looking for coloring rules in which the color is allowed to change at the middle of the crossing, and A will go to A, let's give it a different name, A down B. Okay? So now you're looking for sets B with two operations, so up and down, and there will be axioms coming from Reidemeister moves. And I believe that this is what is called a biquando. So the axioms you will get are the axioms of a biquando. Okay? Okay, that's all I have to say about quandles. Now, I'm a bit worried about even attempting to write more, because everything is barely moving. So freeing memory didn't do it. I don't know what's going on. Okay. I'll try. So the next topic, sort of most of what we said so far was about the dual of knot theory, not really about knot theory. So instead of talking about knots, we talked more and more and more about knot invariants. And I want a small chapter about the knots themselves. So a little bit of, well, I want to tell you about Seifert surfaces, and then about prime decompositions of knots. But let's start from, so the composition of knots into primes. But let's start from Seifert surfaces. So definition, a Seifert, the I didn't come out, a Seifert surface for a knot K is a let me say smooth, because I don't want to worry about topology too much. So it's a smooth, connected, orientable, two-dimensional, I don't know how this happened, two-dimensional surface with boundary, and let's call it sigma, whose oriented boundary is the knot. In other words, such that the boundary of sigma is equal to the knot, and I should have said that the knot was oriented to start with. Right? So, okay, so maybe I'll give an example. Maybe I'll give two examples. Or three examples, if I'll ever get to the point where I can do it.
Did we assume that the Seifert surface is oriented or just orientable?
No, it's oriented. Did I write orientable?
Yeah.
So I want it to be oriented, not just orientable. Sorry. So not only it can be oriented, oh, you're right. Not only it can be oriented, I want it with a choice of orientation. Everything was normal just a couple hours ago. So I don't know what happened. Okay, so a few examples. Let's say the knot, K is the A knot, maybe oriented counterclockwise. So here are two Seifert surfaces for it. One is just the disk. Okay, but with orientation, so I need to pick an orientation on this surface, so I want it to be compatible with the orientation of the knot. Here is a second example. So, if I do the knot in blue, then here is again the A knot. And now I'll just take a genus 1 surface, so a torus with boundary, and that's an equally good Seifert surface for the A knot. Okay? And then here is a strange example. So I'll give the example, by giving the surface. So I'll draw three you'll see what. So these are, oh no, I did it wrong. So these are three twisted bands. So you take a band of paper, okay, and you so you take a band from paper and you give it a half twist. So that's what it looks like. And then I connect the three bands as follows. So I connect the right hand sides to a disc as I wrote here, and the left hand sides to a disc as written here. And if you think about it, so okay, the boundary is a knot, and if I orient the knot so that this is going down, then this is down, this is up, this is also going down, and then the orientation of the surface should be this way on the right lobe and that way on the other lobe. And this is consistent because the bands are twisted. Or said differently, if you color the sides of the surface black and white, then say this side would be black on top, this side would be white on top, and this is consistent because they are connected by twisted bands. Okay? Good. So, theorem. Oh, maybe even before the theorem. So, just a word about Seifert surfaces. About surfaces. So, you may have seen the classification of well, there is a classification theorem for surfaces in general, but let me restrict my attention to the classification of connected orientable surfaces. So the statement is that every connected orientable surface is homeomorphic to one of the following. Oh no. Now again I have to wait. To one of the following. So it's either a ball or a torus or a two-hole torus or in general a G-hole torus. So a G-hole torus would be a thing with G holes. Okay? And we say that this is genus 0, so this is the genus of the surface, and here it is 0, here it is 1, here it is 2, and if you have G holes, then that's genus G. It's nearly pointless. You know what? I'll reboot my computer and we will restart again. Better lose 5 minutes. So please connect again in 5 minutes. Okay? I'm disconnecting the video and we'll start again in 5 minutes. Okay, we're back on. I hope everything will be fine this time. I don't know what happened. Similarly, there is a classification of connected surfaces, connected orientable surfaces with boundary. And the classification is that every surface, so every such surface, surface is homeomorphic to one of surfaces sigma g comma n, where sigma g comma n is basically a genus G surface, so it has G holes in it, and then n boundary components. So these are holes in a different sense, right? These are punctures in the surface, and these are places where you've added a handle to the surface or dug a hole through the surface and connected it to its others, a tunnel through this spherical object and connected it to the other side. Okay? So maybe before continuing, what is so if you believe this theorem, then this surface should be homeomorphic to some sigma gn. So question, this is homeomorphic to some sigma gn, and the question is, which sigma gn is it? Right? It doesn't look like any of the ones I've shown. Okay? So I don't know if we should spend a little time trying to do it. Let's try to do it. So let me slowly modify this surface until you see that it's one of the sigma GNs, and that will be the end of today, so it will be a somewhat disappointing day. So basically, here is our surface. It looks like this. So first step, right? So this is the same. Okay, so the surface is this lobe connected to this lobe with 3 twisted bands. So the first step is let's flip the right lobe like this. So this will untwist the middle the middle twisted band. So we will have something that looks like this. A two-lobe, no, you know what, I should have done it differently. So it will look like right, so again I've twisted the middle, I've twisted the right hand side, so so now I have the two lobes connected by a bridge, and I still have to tell you how these two bands are connected, right? So since I've moved this, since I flipped this over, then this band will be going like this. Wait, which side to where? Let's see, this is oriented this way, so so this way. No, the other way. Right, so I'll have one band going like this. Oh, actually, oh, I think I've drawn the, oh, so you know what? Yeah, so I'm twisting it this way, so one band, but it goes over, not under. So I should have done it this way. Right, and then the other band, again, when I twist the right lobe around, will be going under everything. Oh no, I didn't leave a gap for it to connect. So it will be going, well, but you know, instead of drawing it going under everything, I will draw it going around. So this will simplify things. So it will be going like this. Sorry about this. So I have, the surface has these two parts, this band and that band. But now I want to change my perspective a little bit, and so really I want to think of it as a disc, which I now mark in red, with two bands connected to it. So and if I travel along the bands, so maybe I'll call them band 1 and 2. If I travel along the disc, I see band 1 and then band 2 and then band 1 once again and then band 2. So this is the same as, let's draw a disc with, maybe I need more space, I'm sorry. So let's draw it as a disc with 1, 2, 3, 4 gaps, and then I have one band connecting like this, sorry, like this, and the second band connecting like that. Okay? Now I think I will be better off. Wait, why did I add
That's
a
a
twist?
bonus, yeah.
Sorry, I added an unnecessary twist. I wanted this way. Right. So what is this? Well, okay, a different way to see it. So, okay, so now I want to look at it like this. So here is an annulus. So basically, the stuff I marked in red is an annulus, and I have an extra band connecting one side of it to the other side of it. So a different way to draw it is, well, it's a cylinder with an extra band connecting the top to the bottom, right? But now I can pull the cylinder along this band until it almost closes on the other side. And what I have is a torus, sorry, a torus with an extra band. But having an extra band is exactly the same as removing like a thing that goes around this band. It's exactly the same as removing the rest of this wrapper. So this is the same as a torus with a hole drilled in it. So the conclusion is that the surface I was drawing there was a sigma 1, 1. So genus 1 with one hole, and I'm a little bit over time, and today was a horrible day, but I hope I'll continue and have less technology issues on Friday. So see you on Friday.
Just to